Hello and welcome to the final class of particle fundamentals and fuzzy logic. In the previous lessons, we really tried to cover the basis of rotational vector curves, all the properties we might encounter throughout a particle simulation, as well as the nature of feedback. So in this lesson, we're going to combine all those together in a little bit more advanced application. Because the thing about a shark is we do want to control behavior to some degree. It's not purely a swimming to the target sort of thing, as we can see here. Sharks are known to circle their prey, and they're known to circle their prey pretty wide radius, and then as they hone into their target, they'll circle closer and closer. So we do want to do a bit of a combination of the adaptive feedback we did in the previous lesson to put noise on the target and also apply some rotational stuff into the shark's perception of its target, which will affect its target direction. So let's get started with that. For testing our circular target, the first thing I want to do is turn off anything that could cause the shark to move for now. So I'm going to go into the seeking behavior, disable the velocity, as well as get rid of any ocean current. There we go. And let's view our target vector and target vector absolute. They should be the same if we turn off the noise. So let's turn off the noise. Right now, the yellow is different than the black one, but turning that off, they should be the same. Okay, so now let's add a new VOP, and let's call this rotate target behavior. Adding that in. Now, we've dealt with particle feedback in many of the previous lessons. And in this case, I just want to shore up a concept that we might find useful as the system becomes more complex. And a lot of times we might want the previous value as opposed to just the current value. So in Houdini DOPS particles, we already have a position previous, and that can be really useful compared to the current position to calculate all sorts of things. But what if we want our own? Well, we have to add it in at the start of the system. And here's how we do that. The reason we add in any kind of feedback mechanisms, we can call this feedback attributes. The reason we have to do this at the start is because these attributes change downstream. So if we want to record a previous value, you have to do it before the value is changed. Okay, so here I want to record the position of the target. Let's see, so here's where we're gathering the target vector. And actually, I want to record the straight up position of the target right here. Let's do that. Okay, we can call this target position absolute, meaning that it's not affected by noise or anything like that. Okay, so we're recording that. Okay, so there's our target P absolute. And now what if we want the previous value of the target position? So for that, I'd have to go up before this was set, because this is actually setting this value right here. So going into this, I'm reading this in, and let's set target P absolute previous. And just like that, that's all we have to do. And we should see as the target changes. Okay. So we should have one frame of difference. Scrubbing through that. So here's the one frame of difference from here to here. And then on the very next frame, that should change. If we were to put that after it, then you'd see that they're always going to be the same value. Okay, so the reason I'm recording the target position is so that it makes it easy to rotate a new attribute around it. I'll just get rid of these. And let's go down to our rotate target behavior. Let's start off by importing the target position absolute. And to rotate a vector about this position, we would need feedback so that it can rotate progressively. So let's call this shark circle position. That'll be our vector that we're ultimately going to circle around. Okay, so this is exporting and this would be importing. So here's our feedback loop. And whatever we do to this vector in here, okay. Let's just default the vector to about 2 in Z. And let's rotate this. Okay, about this point. So we also need to give it an up vector. So let's call this shark circle up, defaulting to y is 1. So now let's apply the rotation. So we'll use the digital asset we made in a previous class, the rotate vector by degrees. We want to rotate our shark circle P about the up, the shark circle up. We want to use the pivot, the target position as the pivot point. Let's rotate that by 3 degrees every frame. See if it works, and it works. Now we've got an awful big radius here, and I think we want to be able to set that exact radius. And I also think it's a safe assumption that we're not going to be doing like a crazy up and down rotations. We just want to rotate about flat about the shark circle up. So we could also flatten. And this is the 2 cross products technique we used in one of the previous classes. Okay, so as this thing comes in, I want to set it to an actual distance value first. Okay, so in comes the shark circle position. I want to flatten that on the up axis. Okay, and now I want this vector to be an actual distance. So I'm going to normalize this and multiply that by whatever we want our rotational distance to be. So let's call this shark circle distance. Have it default to 2. There we go. And let's rotate this vector instead. And hitting play, that doesn't look very sensical. It's like it's just stopping at 2 here. And that's because we're dealing with more or less an absolute position. And we want to be dealing with a pure vector in order to be rotating around this vector. So first, let's just subtract what would be the pivot point going into our flatten. And then the result of this, we'd re-add it. Okay, and now let's see if that works. There we go. So now it doesn't matter where it starts off at. It's rotating with a distance of 2, and our target changes, and it just keeps rotating. Okay. And let's encapsulate this and call it a line. Okay, so we're aligning the shark circle position to the rotation axis before it rotates, and it'll always have a distance of 2 as it circles around. Now, let's make that a little faster. Okay, so spinning around there, and then as the target switches, okay, we might see an abrupt change. And that's not, even though the shark is going to adapt its position, it might want to instead take this route instead of this route as something adapts. And that might be really apparent in some situations. We don't really want this thing always to be rotating counterclockwise. Now let's get the direction that this red dot, this circle position, is traveling. And so we can have the shark make a decision as the target position changes as to if it's the most efficient or least efficient way to go is circling positive or circling negative degrees. So for that, we need some feedback. All right, so to get the direction between two vectors, we would simply subtract. So I'm going to subtract the shark circle position from the previous circle position. How do we get that? Well, for that, we need to get some feedback on the shark circle piece. So I'm going to go up here, up to our feedback attributes, and let's record the current shark circle position and the previous shark circle position. Okay, so that'll be the previous. Okay, so we should get some lag. Okay. Okay, so this 328, that should go here on the very next frame. Yes. Okay, so we've gotten the previous shark circle position. And we're going to subtract those. And now let's export this as shark circle direction. And let's view that as a vector. Let's go maybe dark purple. Okay, so we can see that this dark purple line right here is going in the same direction that this red dot is going. And we also need to know if it's rotating this way or this way. We need to know what those values are. So currently we're just rotating in the positive direction. So we'll call this positive rotation. And let's call this negative rotation. And let's get a rotate degrees happening. Okay, so positive rotation of degrees or negative rotation degrees. So we're going to do this operation twice, and it really isn't that much overhead, but this is going to be a good comparison. And we can say, is it going in a shorter distance to this direction or a longer distance in that direction? Does it have to turn less or turn more is really what we're after between this and this based on this shark circle direction. So now bringing the shark circle direction back in before it's set, and let's get the dot product. The previous position subtracted from the positive rotation. Let's make a preview utility for that so we can see what's going on. I've gone to right where the target switch is. Okay, so here, if we just look at the test, it's in the opposite direction as this. You can see a bit of red there. Okay, and it's not exactly opposite. It's mine ever so slightly different than this purple line, because this is the previous one and this is the next one. And we're going to compare that once it's normalized in angle to the incoming circle direction on the previous frame. And we're going to say, should you rotate this way or should you rotate this way? What is the closest mechanism of rotating? So I'm going to get the shark circle direction and our subtraction there. And let's get the dot product of that. Okay, let's encapsulate this. We'll call this dot positive. And then we also want to test the dot negative. And we really just want to get which one is rotating in the positive direction according to our shark circle direction. So positive rotation, and this would be the negative rotation. Okay, and let's just compare those. So if the dot of the positive rotation is greater than the dot of the negative rotation, then we want to use the positive rotation. Otherwise, we want to use the negative rotation. So it did 2 decisions on every frame, and it's picking the one where it's traveling in the right direction according to the shark circle direction. So let's plug this in. So now it should be allowed to rotate both ways. And in this case, it should actually be less than. Okay, so play that and watching it rotate. Let's also preview. We'll call this dot. Right here. So rotating clockwise. And we can see it circling around. And then right as it gets to the point where it's less efficient, it will start rotating the other way. Okay. So this is really the difference. This feedback is really the difference between why we couldn't just rotate a target around at SOPS level. It's because here we're able to dynamically adapt, and this could be based on lots of factors in the environment. Okay. So now let's get rid of this abrupt transition. So here it's going to just jump as it transitions. And I want this distance to be in a constant state of adaptation while the target switches. So anytime we go on adaptation, we need feedback. So what do we want to adapt? Well, we want to adapt the distance. Okay, so that would be shark circle distance. All right, so use this node, export when input is connected. And now I'm going to cause a feedback loop here and update this value dynamically. Okay, so what are we going to update that with? Well, what we want to do is we want to calculate as the target moves, we want to negate that travel distance. Okay, so we'd have to get the previous target position and the current target position. Okay, so here's our feedback attributes. Here's the target position absolute, and here's the target position absolute previous. So let's just subtract those 2 distances from the circle position. So there's our circle position. Just going to put this guy in the middle. And I'm going to get the distance of each one. we go. To get the change in distance, we'd subtract the current from the previous. And that'd be the difference. Okay, and now let's just add this to shark circle distance. See what happens now. It should maintain this distance throughout. There it is. So it's actually ignoring our parameter. Let's see if it maintains its distance as it changes, and yes, it did. See, so this changed, but the circle, actually the target here, see, it's staying in the same spot, but now it's rotating around a much wider radius. And as it changes again, okay. And it's most likely just going to keep getting bigger and bigger because it's not very likely that the target's going to move closer to it if it's already spinning around here. So let's reintegrate a target distance and have our circle distance be in a state of adaptation to try to achieve that target distance in light of this changing distance scenario. So let's put some feedback, some adaptation on this float. We went over this in a previous class, and it was encapsulated in the asset adapt float with feedback. Okay, so our adaptive value will be this value. Let's see, so the target value, let's say that's a target distance of 1.5. The target minimum is 1.5. The target maximum, let's say it's 6. The adaptation, let's put that to 0.2 and mixing in to get a smooth transition. Okay, so this should be the distance it will always seek to adapt to. And it'll update this kind of under its feet. So it'll always try to get closer and closer to 1.5. And it's spinning around, but it should be gaining some ground here. Let's see, let's have that adapt a little more. Let's make that quite a bit stronger. Maybe adapting 3 units per second. There it goes. So it's always zeroing in on its location here. And here we can see that at work. Okay, getting pretty cool. All right, so you might notice a strange thing that happens. So as this adapts to a very different target. Okay, see how it really increases its speed? Okay, and that looks fairly artificial and unnatural. So we'd also want to calculate out the difference in distances and have that cancel itself out as this motion is circling around. So to get the percentage of distance change, we'd have to divide. So dividing the previous distance by the current distance, and we could cause a feedback loop on our speed. In this case, I've called it shark orbit deg. Okay, so here's our feedback. Let's multiply this by the change. And we're going to get a slow degradation of time of speed as the target changes from place to place. So we would want to adapt to keep up the current speed. And we could set these target minimum and maximums based on the range that we'd like to spin. So for now, we'll just put it to 9. And let's get some values here, adapting 2 degrees a second. Okay, of spin. And now it should always try to maintain about 9 degrees as we had it. And our distance. Okay, almost there. Okay, we're getting some really nice adaptive circling behavior, and it's always picking the closest path and trying to reach its equilibrium in both speed and in distance. So now the fun starts. Now let's use some curves, and based on an external factor such as the shark, the distance of the shark, we could make it circle closer and closer and get that kind of broad approach and then closer circling. We could also have it circle faster or slower based on how close the shark is. So let's get how far away it is. So because this is all going to be done before we compute the target, we need to abstract that one level. And I want to go way back up to where we're getting the target vector. And let's make an absolute distance. So all of the other things can be based on that. So we'll just do a length here. Okay, so position, subtract. Okay, so the length of this vector would be the distance the shark is away from its absolute target. Call this target distance absolute. There we go. Okay, so that's being set. And going downstream, so now let's import that. Target dist abs. Okay. And here I just want to clamp that to the lowest it can possibly go, because we don't want the shark to orbit at too small of a distance. So there's 1.5. Let's make that minimum shark, or minimum orbit distance. Minimum orbit. Okay. Maximum should be pretty high. Okay, and I always want the shark to be getting nearer if it's not clamped at this minimum value. So I'm just going to multiply constant. Let's multiply by about 60%. Okay, so now using the distance, that'll dynamically control the shark circle distance value. So I'm going to put that into target value. The target minimum, well, that should be this minimum. Target maximum, let's say that is the actual distance. And adapting, let's adapt by 2 units per second. So now if it's far away, and you see it's circling at about 60% of the distance of the shark to the target. And if the target changes, then now it's adapting to make a smaller rotation distance. And the shark will of course be getting closer and closer, and that'll cause it to circle in on its prey. Okay, let's also use the target distance to control the orbit speed. So for that, we can fit this to a range. And let's fit that to shark distance high. Say orbit distance high. To 0 to 1. We could use a ramp here if we wanted to. And this will be orbit distance rate curve. Okay. And then let's fit this to our desired rates. So we should already have one in here. Okay, so here's the orbit speed. Okay. Right here. So I'd set that to 9. So there's the minimum orbit speed. And we probably want a much smaller orbit speed. And let's do a maximum as well. Okay, so go from 0 to 1 to our minimum orbit speed and our maximum orbit speed. Okay, there we go. We also know the minimum and maximum values now that we're going to interpolate into. So let's try that. Okay, so let's set those parameters here before we go much farther. So minimum orbit speed and maximum orbit speed, let's set that to a bit more conservative value for now. That's the minimum distance, orbit distance high, say that's about 5. And let's give this an exponential ramp, or an ease in, ease out. Okay, and now let's activate the velocity. Go. And here we are. So we can see that the ball is getting closer as the shark is near. And we'd home in on his prey. Okay, so now the final step is just to make the shark dependent on this vector. So instead of this target vector, in our rotate system, let's overwrite what's driving the shark, which is target vec. Vector, when input is connected. Okay, so we want our target vector. So here's the circle's position. And let's get the actual position. And subtract. From the circle position. Target vec. Okay, it's the wrong way. There we go. Okay. And we have rotations and circling behavior. Okay, I think 1.5 circle distance might be too conservative. So let's try 2.5. Orbit speed, let's make that a bit smaller. And we should start to get some actual rotation behavior. Okay. Now to add noise to that. So we want to add this noise on top of our rotation behavior. So at this final step, let's just add in a variable for the noise. Okay, so I'm going to put this above, enable it, and here, out of the very last step before we add to absolute vectors and positions, the result of our noise, I'm going to call this noise underscore p. And here we can just add that in as well. So now here's the rotational. And then we are applying some noise per shark to those rotations. Okay, let's increase the shark count. So here I've got a scatter, and let's just increase that. Let's add in the ocean current. Okay, so we have some cool circling behavior. All right, so that was advanced, but it just goes to show that there's really, within a dynamic environment, you can do just about anything to your positions and your rotations and your normals. You can give these sharks whatever kind of behavior you might like based on how you think they should act. Okay, so let's see what deforming sharks look like. And here you can see the final result of the deforming sharks. So all of the tools and nodes and settings here are the ones we've done in the course. I'd encourage everyone to make their own variations or perhaps take on different crowds or different particle behaviors to really solidify those foundations. Any variations can simply be done with the source particles with any fuzzy attributes along with target destinations. Okay, so even though this course was fairly low level with all of the low level attributes, I hope everyone got a lot out as far as vectors, rotations, adaptation, use of curves, variation, and different behaviors based on environmental stimuli. I hope you enjoyed the course, and I hope after watching you have a more fundamental understanding of particles and fuzzy logic.